Hi, good afternoon, everybody. So today we'll talk about simplified neuron models or low-dimensional neuron models. So if you look at the kind of models that we have looked at in this course so far, right? Our first neuron model that we looked at was Hodgson-Huxley model, right? Which was motivated by the biophysical analysis of the axonal currents in the giant squid axon. So then from there, it's a point neuron model. Right, from there, we went to even more detailed neuron models, right, where we looked at dendritic processing, axonal processing, right, synaptic transmission, and so on. But the ultimate objective of this course, and in fact, ultimate objective of neuroscience itself, is to understand phenomena of the brain at large scale, right? And in fact, my personal complaint about the way neuroscience is going on is we don't seem to solve many problems, right? So problems faced by people. That means solve diseases, treat diseases. Right. For that, we need to understand how the disease works. So, which means we need to understand how the brain works at the large scale, and which we don't. And we don't understand how brain works at large scale. We have very poor understanding. And for every structure, you have lots of theories, and there's no consensus. Right now, as you know from whatever systems understanding that you have from your respective fields or branches, that when you build a system, the basic unit of the system must be sufficiently simple. Only then, with that as a building block, you can construct complex systems. Right? If you look at matter, the simplest atom is a hydrogen atom, which is very simple. Right? Or if you look at, say, a study of motion, right? Your simplest motion equations are very simple. Whether it is uniform velocity, uniform acceleration, right? You could study it in high school level. Similarly, if you look at the simplest circuit theory, the simplest equation is V equal to IR, Ohm's law. And then you look at inductance and capacitance and build circuits and so on. So the basics are very simple. Whereas if you look at the way we have been studying neuroscience models so far, the basic model itself, which is the Hodgson-Huxley model, is so complicated. It has four variables and four differential equations, all the four highly nonlinear, and so even to analyze it, it's very hard, right? Because all that we have done is some numerical simulations. We saw some patterns, but that's not science. That's just that's very empirical. So if the basic building block itself is so complicated and so opaque, right, so difficult to analyze and understand, then the larger systems that you construct out of such basic units will be even more opaque, okay, which is not good. That's not how science should proceed. So seeing these problems with the Hodgson-Huxley model and the way the field has been developing, so people have suggested simplification of the Hodgson-Huxley model. Right, that's how the search for, you can say, the search for some kind of a universal neuron model, a simple model which can explain a lot of things. Not 100 models for 100 different things, but one model which can explain a lot of phenomena. So that kind of a search for a simple neuron model has begun like that. And one of the first such models that was developed, which was actually derived from the Hodgson-Huxley model, was the Fujinogo model. So let us see how it works right now. So this began with Hodgson-Huxley, then went up to more complicated or more detailed cases. Now we begin the step-down process to less detailed or simpler models. So, like I said, the Hodgson-Huxley model is the earliest model of action potential generation, right? In the neuron, it's a point neuron model, right? And this action potential is generated because of the voltage-sensitive dynamics of sodium-potassium channels. But there are lots of other kinds of channels, and different neurons have different kinds of channels. So you can, Hodgson-Huxley model is only one kind of a neuron model. So in fact, in the last demo class, you might have seen in the simulator, right, in neuron simulator, you can put together all sorts of different neuron models with all sorts of ion channel combinations, right? You'll have a whole zoo of neuron models, but that doesn't give you any insight about what is a basic neuron, what is a fundamental neuron, right, from which you can derive other things. So it becomes very empirical and non-standard. So the combinations of these channels can give all sorts of neuron models, and so therefore there's a need to simplify neuron model and come up with something fundamental. Okay, so sorry. So one such reduced model, one of the first reduced models of that kind, something which has fewer variables and milder nonlinearities, right, is the Fujinogo model. So how do you do that? So Fujinogo model is a two-variable model, and which is constructed by reducing the four-variable Hodgkin-Sley model. And what is the advantage of two-variable model? You can analyze it on the phase plane. You can apply all your phase plane techniques and analyze what is going on. Right? You can find out, for example, for what current does it oscillate. So if you look at the Hodgkin-Sley model, one of the basic properties of a neuron is when the current input is less than a threshold, there is no response. That there are no action potentials. And when the current input crosses the threshold, there should be action potentials. So simple threshold phenomenon is very common to most neurons, right? And Hodgkin-Sley model does show that that's one of the nice things about it. But can we, for example, preserve that basic property of a neuron, right? And but come up with a reduced model, right, by simplifying the Hodgkin-Sley model. So that was the motivation behind uh, Fujinogo model. Now, Hodgkin-Sley model, as you know, is described by these four equations. So first is the voltage equation. So if you look at the original circuit, right, you write the voltage equation for the membrane voltage, you get the first equation. So then you have three gating variables, M, H, and N. Right, M and H are part of the sodium channel, and N corresponds to the potassium channel. Now, the gating dynamics, right, is depends on the functions, alpha beta functions. Each of them has two functions. And alpha beta are the functions of again membrane voltage, and that's a highly nonlinear function. So because of this, all the four equations are coupled and are highly nonlinear. So the question now is, how do we simplify this? We need to somehow get to two. Because once you get to two, you can go to the phase plane, and there's a lot of advantages. Now, one thing that people have noticed or made assumptions to simplify the system of equations, right, is to notice that the timescales of M, H, and N are not all of the same order. Okay, so that gives a scope for simplifying the system. So one other thing is the time scale for M is much smaller than that of the other two. That means, so basically there is a standard technique where we have a high dimensional system with lots of variables. That means each variable is described by a differential equation. So they tend to segregate the variables in terms of fast variables and slow variables. Or sometimes very fast variables, very slow variables, something in between. Okay, so why do we do that? So that gives a scope for simplifying it and getting rid of differential equations. So for example, if a variable is too fast, like in this case, the variable dm by dt, variable m is governed by an equation like dm by dt is equal to all that. So you know that we can also write this as some kind of tau into dm by dt is equal to minus m plus m infinity, right? We know that there are two ways of writing the same equation. So when you write it in that form, the tau m, so I'll just write it here. So tau into dm by dt is equal to minus m plus m infinity. Yeah, this is m infinity. Okay. And these two equations are equivalent. So when you write in that form, the tau defines the time constant that tells you how quickly does m approach m infinity. If tau is very small, it means m approaches m infinity very fast. So we'll just assume that at any given instant, m is approximately equal to m infinity. Just if tau is small, this whole thing becomes approximately 0. So m becomes approximately equal to m infinity, which means the variable is quickly attaining equilibrium, right? Because m infinity is itself a variable. It depends on the voltage. So as m infinity varies as a function of voltage, m is thought to quickly approach m infinity, and right, because tau is small. So therefore, if you can do that, then you can just assume that m is equal to m infinity. And if you do that, I can get rid of the differential equation, and then you are left with a static equation. Okay, that's a major advantage. So that is one kind of simplification. Then, so if a variable is too fast, you can kill it in one way, right? And again, if a variable is too slow or doesn't vary much, you can kill it in a different way. How do you do that? So in this case, they found that h variable doesn't vary much or varies too slowly. So they just assume that h is a constant, and that is h is equal to h naught. Okay, so m is equal to m infinity, and sorry. and H is equal to H naught. So therefore, you can get rid of those two differential equations, and then you are only left with the voltage equation, Vm, and the N equation. This is H. Okay, so you are left with only two differential equations. But how do you make this conversion? So people have worked it out, and because it's a very highly nonlinear equations, they worked it out and even simplified the nonlinearities. So for example, if we have a complicated nonlinearity which is shaped like an N, right? So suppose you have an N-shaped nonlinearity which is made up of exponentials and tan h and things like that, because these are the kinds of functions that you see right in your previous equations, Schwarzschild and all that. But this I can also express as simply as a cubic. I don't need tan h. It's an approximation, but it's a good enough purposes because we only want to understand the dynamics of the neuron qualitatively. Okay, so like that, people have simplified it and arrived at these two equations. Okay, the first equation, which is like the voltage equation, and these are dimensionless quantities, these are slightly abstract quantities, but corresponding to those original quantities. So for instance of Vm, we have this small v or small v here. So dv by dt is equal to f of v minus w plus Im. Im or Ia is the external current, and f of v is has this kind of a shape, and that is given by this cubic equation. So v into a minus v into v minus 1. So a is some number between, oops. So 0, 1 is some number in between. Okay, so you can easily plot the shape of this function. So it has 3 zeros. One here, right at nu is 0, there is a 0. At a, there is a 0. At 1, there is a 0. Now, so between if v is less than a, right, and greater than zero, this part is negative. Okay, so it is like this, and therefore it has positive here because under 0 here. So it goes like this. So f of v, f of v looks like this. Okay. Yeah, so I don't know why this thing has come. Yeah, so that is the first equation. The second equation is dw by dt is equal to bv minus rw. Now, w is not exactly the n variable because we know that we've got rid of m and h variables and we left with only n. W is a transformed variable, but which is related to n. Okay, and they have simplified the nonlinear, got rid of all the quadratic and above nonlinear terms, and have just taken the linear terms. So you have a bv minus rw, and both b and r are positive numbers, right? And also they are assumed to be small in magnitude. Okay, so both b and r are positive, and they are less than 1. Okay, so like I said, V is analogous to the membrane voltage and W represents so because it is absorbing, so all the M and H variables also, it represents the dynamics of N variable. So now this is a system, right? How do you analyze this? So the first thing that we do is we have to plot the phase plane, right? Plot the null lines and find out the fixed points, right? So this the null plane of the first one, simply what you get by set to 0. So that means W, if this is 0, W is equal to FV plus IM or IA, external current. And the second one is GVW is 0. That means BV minus RW is 0. So the first equation is simply W is equal to a cubic function plus a constant term. So because this second you can write as W is equal to a cubic function plus a constant. Okay, so that gives you this kind of a thing. And the second one, again, you can see here, you can say W is equal to minus B by R into V. So that gives you a simple straight line. Okay, so you can see that if you plot both on the same axis, right? It will intersect, the straight line will intersect this curves at the origin. So somewhere like that. Okay, so that is, you have only one fixed point in this case. So you need to study the stability of that and try to understand how the system behaves, right, when you give some input. So how do you study the stability? You have to find out the Jacobian and find out eigenvalues and all that. Now, Jacobian of this is, so this whole function I'm calling it CalF of VW. And then this function is G of VW, right? So you take dou F dou V and dou F by dou W. This is dou G by dou V and dou G by dou W. If you do that, so this dou by dou V whole thing is simply F prime. So you get that here. Dou by W of this whole thing is simply -1. So you get it here. Dou by dou V of this one is B, and dou W of this one is -R. So you get it here. So now to find out stability, right? You know how to find stability from the determinant and the trace of this matrix. The determinant is this times this, to get this, and trace is this. So from this, can we find out, right? What is the sign of the determinant? What is the trace of the determinant? Based on that, you can find out the stability. So now, if you forget about the distinction between spiral and node, right? So if you know that. So this is tau axis. So above it is unstable, below it is stable. On left side it is all saddle. Okay, this is the broad. This thing you have. Further you have spirals inside the parabola and nodes outside parabola. But let's ignore that for now. We'll just look at stable and versus unstable. So for delta less than 0, you have saddle. For delta positive and trace positive, you have unstable, and etc. So let us see that. So delta positive and tau negative, it is a stable fixed point. Now for that, so this quantity must be positive. This quantity also must be positive. So this quantity must be positive, means this minus should be greater than minus b. Okay, so that means multiply both sides by -1. You get this is less than b, and this is less than b by r. Now note that b by r is a positive quantity, because b and r are positive, and also we assume that although b and so b and r are positive, but we assume both are very small numbers. But b by r doesn't have to be a small number. That slope can be big, but individual quantities b and r are small. This is the assumption. So now, so when this happens, right, delta is positive. Okay, so that is one observation. So geometrically, what does it mean? F prime is the slope of the F null line, right? Because so this is F prime, right? Is the slope of the F null line, and B by R is the slope of the Y null line. So this is B by R, right? Because this is V equal to B by R times W. So geometrically speaking, if the slope of the F null line is less than the slope of the W null line, the determinant is positive. So that's one observation. So then what about tau, right? What can we say about tau? So tau is positive when F prime minus R is greater than 0, or when we also assume that B and R are both very small numbers. So approximately F prime is greater than 0. So F prime is positive, right? That means tau is positive. So this is our basic observations. So based on that, so let us see what happens as the external current IA is gradually increased. First, let us see what happens when IA is 0. Okay, so the phase plane will show below what happens when IA is 0, right? You can see here that this is what happens when, this is how the phase plot looks when IA is 0. Okay. So this is what happens when IA is 0. So the fixed point is at the origin. Okay, and yeah, so right? We look at the stability of the origin, and we look at this. So you can see that here, slope of the epinal plane, right, is if it is greater than the slope of epinal plane. So the epinal plane is less than by r. Okay, so in fact it is less than the double null plane because slope of the epinal plane is negative, and slope of the so slope of the v null plane is negative. Slope of the double null plane is positive, right? So therefore, in this case, epinal plane is less than the slope of the epinal plane is less than slope of double null plane, right? And therefore, this is negative, and therefore tau is negative. Okay, so origin is a stable fixed point, right? So delta is positive, and origin is a stable fixed point. Now it is stable, but something interesting happens. The approach to stability. So stability means it's what this stability analysis that we have done by simply looking at eigenvalues. That we have done it indirectly using by observing delta and tau. It shows local stability. So that is, if I start from anywhere nearby the fixed point, I'll go towards it. But what about global behavior? If I start from anywhere in the phase plane, how do you approach it, right? So do we just approach it from starting from anywhere in the state space? Do I just approach it the fixed point just like monotonically, or is there more complicated behavior? So let us see that, right? So for that we need to understand the global structure of the vector field, right? And for that we need to do what we have done before with the phase plane. That is, we need to understand what is the flow like all over the phase plane, right? So we know that on the v null plane v dot is 0. Right now, we need to find out what happens above the v null plane, what happens below the v null plane. So, if you look at the original v null plane formula, right? If you look at this formula, right, when this is 0 on the v null plane, but if I go above it, that means I'm increasing w. Okay, if we increase w, you can see that this quantity becomes negative. So that means above the v null plane, v dot is negative. So, therefore, contrarily, below the v null plane, v dot has to be positive because w is decreasing. Therefore, this will be positive. Okay, so let us plot that here. Above the v null, so I already plotted it here. Above the v null plane, v dot is negative. So that means, so you divide this whole thing. So the two null plane divides the whole plane, phase plane, into 4 parts. One is this part. The second is, so this actually goes up like this. Okay, so therefore this is another part. Then this straight line goes like this. So this is a third part, and so this is the fourth part. So in this entire space above the v null plane, v dot is negative. So v dot is negative here, but in this part, and also here. Now, if you look at the w null plane, and for w null plane also, right? So this is the w null plane, and b and r are positive. So on the w null plane, this is 0. So if I go above the w null plane, that means I'm increasing w. So this becomes more negative. So on the whole, this thing becomes negative. So above the w null plane, my w dot is negative. So let us use that in this plot. So this is the w null plane. Okay, and this is the v null plane. So above this w is negative. So we have said that here. Therefore, here also w is negative. And so below that w is positive. So that means in this part w dot is positive. In this part w dot is positive. So once you have this, you have roughly an idea of how the flow looks like. So in this part, v dot is negative, w dot is positive. Okay, so there is flow is to the left and slightly upwards actually, slightly upwards. Why is it slightly upwards? Because because b and r are small numbers. So w dot can change its sign, but the magnitude is generally much smaller than v dot magnitude. So that's the main difference between v dynamics and w dynamics, because b and r are small. So it is here the flow is leftwards but slightly turned upwards. So here also flow is leftwards, but slightly turned downwards in this part. Here, V dot is positive, so once you cross over here, the sign changes. W dot is negative. So turn to the right and turn downward, so it will be kind of like that. Right, and here V dot is positive, W dot is also positive. So both are, this is turned to the right and up and slightly upwards. So you can see roughly there's some kind of a circulation going on, but there is no limit cycle there because this is a stable point. Okay, so only thing is it's stable, but we want to analyze how we approach that stable point if we start from anywhere in this state space. Now let us look at two conditions, right? Let us figure out what is the nature of the approach as we approach from different parts of the state space. Now, since we said that the W dot variation is not much, right, because it is small in magnitude, let us focus on V dot and let us focus on certain initial conditions. Okay, so let me take V from within this part. So between 0 and this is A, right? If I start from here and here, what happens? Or if I go from beyond this and start from between A and 1, what happens? And I assume that initial W is 0. So let us start with initial condition. V dot is between 0 and A, okay, or V dot is between A and 1. So these are two cases. And W dot, we just assume to be 0. So for these two initial conditions, let us see what happens. So if I start from here, so anywhere on this interval, I'll take P1 as a representative point of that. So what is the flow direction here? So here in this section, P dot is negative, W dot is positive, but small in magnitude. So kind of it has slightly upward flow, but it is mostly turned leftward. So the point will drift towards left, right, and go towards the origin. So let us see that here. If I start from here, let P1, call this P1, in this interval, it just kind of goes towards 0 and stops there. So this is a stable point. Now let us look at the next case, P2, right? P2 is between A and 1. Okay, and if I do that at this point within this region, so you know that V dot is positive, so it won't move towards origin, it will move away from that. So now you notice that something funny is going on, because if this is a stable point, and that's the only stable point. In fact, that's the only fixed point in the whole phase plane, right? We would naively imagine that all the points from everywhere in the phase plane will simply move towards it monotonically, but that's not what is happening, right? If you start from in this part, you are pushed away from the origin, although it is stable, and that's the only fixed point. Okay, you are initially pushed away from it, but something interesting happens when you reach the null plane. So this is the V null plane. So once you go there, your horizontal motion goes to 0. That is, V dot becomes 0 on this thing, so you don't move any further. So similarly, even if you start from somewhere beyond this, right? So in this part, V dot is negative, so therefore you will move in this direction. Okay, so kind of you are moving towards this line from both sides. If you start from here, you move towards it. Start from here, you move towards it. But once you go to the line, V dot is 0, but that doesn't mean there is no force acting on the point, because W dot is still non-zero. W null plane is here, so W dot becomes 0 only when you are on this line. But elsewhere, everywhere else, W dot is small in magnitude, but it is not 0. Right, so therefore, even when you're on, when you are on the V null plane, that is when W dot starts acting significantly, right? Because V is completely suppressed, V dot is completely suppressed. So W dot in this part, right, so here you are below the W null plane, so W dot is positive, right? So when you are here, W dot will be pushing you upwards. Okay, so when you start from P2, you come up to this point. Once you reach the V null plane, your V dynamics, V dot stops acting on you, and W dot pushes you upwards. So this thing goes on. So if you get off it a little bit, V will push you onto the line again, onto the null line again, and W will push you up. So this funny situation goes on until you reach this point. So beyond this point, if you climb up again, right, you're moved leftwards because V dot here. So once you cross the line, V dot moves leftwards, right? And so you don't come. So once you go up to this point, after that you don't come back down along this line. You get off this null line and continue to move, right, leftwards. And so this goes on and on. So once you are off the new null line, see, as long as you are on the new null line, the only force acting on you is W dot force, right? But once you are off the new null line, then only significant force acting on you is the V dot force. But W dot is insignificant once you are off the V null line. So in this part, my V dot is negative, so I keep going leftwards. Okay, so I cross the W null line. So that nothing happens. When you cross W null line, W is anyway insignificant. W dot is anyway not acting on your motion once you're off the V null line, so nothing much happens here. So you keep on going, right? Only thing that will happen is so W dot is positive here and negative here. So your flow in this part will be slightly positive upwards. Here it will be slightly downwards, but otherwise it will be mostly horizontal and leftwards. So you keep on doing that. You go all the way to the V null line again. So you reach this point. Okay, and once you get there, now once you get to the V null line, again something interesting happens. So this is your V null line. So once you go to V null line, the only force acting on you is W dot. Now in this part, right, you are now above the W null line, so W dot is negative. So you are pushed downwards. Okay, so you have a very interesting situation. You have to stay on the V because if you move to this side, you'll get pushed off just like this. You move this side, you get pushed off like this. But vertically, there's a force acting, which is W dot, right? So you keep on moving downwards, and you go to the origin and you stay there. You're trapped there. You can't move anymore. Okay, so although there is a single fixed point, and that is a stable point, and that's the origin. Depending upon the initial condition, you have very strange, very different kinds of approach to that point. If you start from a point less than this value A, you simply move towards it. And if you start from something above this, the system shows a huge excursion, right? It goes, even if you cross A slightly, right, it goes all the way up to here. This is 1, so this maximum point, and it goes this thing. So in fact, we can easily visualize so what this motion will be like as a function of time. So if you look at this this as a, and show voltage as a function of time. So this is A and this is 1. If I start from some value less than A, right, I'm just going towards 0. So your variation will be like that. Okay, so nothing very interesting. But if you start from a point which is greater than A, so A is here, 1 is here, even something like that. Now immediately you don't come back like this. Now you go all the way to the maximum point, and then come to 0. Okay, so once you cross that threshold, this subsequent motion of the system is no more in your control. It becomes independent of the initial condition and strictly always goes to that 1, right? So it has a standard amplitude the moment it crosses the threshold, right? And then after that it falls off on its own, right? Comes back to 0. So this behavior, it looks like the classic action potential behavior. Okay, and so how do you produce this, right? I'm looking at 2 different initial conditions. So the way you can produce initial condition is to this V dot equation. You have f of V minus W, you have plus I. IA is taken as 0. So right, but thing is, to produce this initial condition, you can imagine that IA is 0, but you can think of it like a pulse. So initially I just give a pulse and remain. After that it's 0. Right? Its long-term value is 0, but I give a pulse initially. So then that pulse will kick V right to some point. Now, if the pulse is somewhat small, the V may not be able to cross the threshold A. Then it just slip back towards origin, which is what we saw in the previous picture. Okay, but if the pulse is strong enough to kick V beyond this threshold A, then immediately it shows a standard behavior because this trajectory, right, what you see after this point, has a standard shape. This is a standard curve, this whole thing. It has nothing to do with the choice of the initial condition. Okay, so this is, you get very beautifully this action potential like behavior in a very simple system. It's much simpler than Hodgkin's model, and we have, you know what is going on. And you also see some kind of a threshold behavior. Where is the threshold here? The threshold is coming because of this. Now, this is what is nice about this model, because if you look at the Hodgkin-Huxley model, right, there also we saw threshold behavior. So we saw that in fact that there are two thresholds which you might have observed again in your assignment, right? You have first threshold where it shows a finite number of action potentials, right, and the second threshold where it shows continuous firing, right? But we have no idea how this threshold, what is it about the system parameters that determines these thresholds. It's all very complicated. Whereas in this model, you can very easily see that it is this value A that determines threshold of firing, right, and determines when the action potential will be produced. So you see the same thing in this simulation. So we have a MATLAB program which gives you this, right? So these are the two null clients for IA equal to 0. So this is the fixed point, and when I give V initial V as less than A, so A is 0.5. If initial V is less than A, then it will just come back to 0. But if initial V is greater than A, then it goes all the way to 1 and then fall back to 0. So resembling action potential. Right. So now how about limit cycles, right? Under what conditions do you get limit cycles? Now let us consider what happens. So what you would expect to see is as you increase the input current, right? In the previous case, you have just seen a pulse current. If you give a pulse, what happens? But as you increase the input current, does the neuron suddenly start showing oscillations, just like the continuous firing activity of a Hodgkin model, right? For beyond some threshold current. So let us see that. So first of all, so as you increase, so let us look at this. As you increase the current, right? So your V null client is f of V minus W plus IA. So as you increase the current, this whole V null client is lifted up. Okay, so I assume that V null client is lifted up, and so actually, sorry, they should be through the origin. This line, I need to draw this line like this. It should go through the origin. Okay, so V null client is lifted up because IA is now some positive value, and so the intersection. So earlier, right, in the previous case, for IA equal to 0, right, for IA equal to 0, the null client and the V null client and W null client are intersecting like this. Okay, so you can divide the V null client into 3 branches. From infinity minus infinity to here is first branch. From the minimum to the maximum is the second branch. I'll tell you why these points are significant. These are important boundaries for dynamics. Then from this point further all the way to the positive infinity, this is third branch. Right? Okay, so let us call this 1, 2, and 3. So in the previous case, where you saw this kind of action potential generation, single action potential generation, when I equal to 0, right? The W nuclear and W nuclear are intersecting in the first branch, branch number 1. So now consider what happens when you increase the input current such that the intersection happens in this part, right? Right in branch 2, right? What happens there? So even in this case, you can again apply our arguments and notice that above the V null plane, V dot is negative here. Below the V null plane, V dot is positive here and here. So above the W null plane, W dot is negative. So here and here. And below the W null plane, W dot is positive. So that is here and here. So if you plot this in this part, right, V dot is negative, W dot is positive. So it goes upwards, right, and upwards and leftwards. Here V dot is negative and W dot is also negative, so it goes leftwards and downwards. Okay, and here V dot is positive, W dot is negative, so it goes rightwards and downwards. Okay, and here V dot is positive, W dot is positive, so it goes upward and rightwards. Also, again, here also same principle is valid. That is, W dot can change sign, but it is small in magnitude compared to V dot generally. So here also you can see some kind of a circulation going on around. This is the fixed point. You can see some circulation going around the fixed point. Okay, so what about the sign of the fixed point? What about the stability of the fixed point? Let us see that. So in this case, you can see that in the previous case, so in the previous case, if f prime is less than b by r, right, delta is positive. So let us see that f prime in this case is earlier f prime is negative, so it is obviously less than b by r. But in this case, f prime is positive, but it is still less than b by r because slope of b by r, slope of the terminal plane is more than, right, the slope of this point, this segment. Therefore, the first condition is still valid. Therefore, delta is positive. Okay, so but what happens in this for the second condition is tau is f prime. In the previous case, when we were on this segment, right, the slope of the V null plane is negative, but in the second segment, slope is positive. So therefore, when f prime is positive, it means tau is positive. When tau is positive, it means the point is unstable. It's actually unstable focus, but we're not proving it here because that requires more detailed calculation. Right, so that is the significance of looking at these three segments. Right, in this segment, the slope is negative. In this segment, the slope is positive. In this segment, slope is again negative. So we go from maximum point. Okay, so because of this difference in this second segment, this intersection point becomes unstable, and therefore you don't have fixed point behavior. And you also see this current, right? So we are not going to do actual, we are not going to apply Poincare-Bendixson theorem and all that, right? We'll just show that there is circulating flow around it. And if you, so this is the MATLAB plot of the same thing. So if you now simulate the system, right, for these parameters, you can see that the output of V, the output V is now no more action potential kind of thing. It's a continuous action potential. It's continuous firing. It shows oscillations, and in fact, these are limit cycle oscillations. Okay, and this is very similar to what we saw in case of Fujinogo model, when you give sufficiently high current where the neuron fires continuously. Okay, so then as you increase current further, right, you start intersecting in the right branch. Okay, so let us break here and analyze the two more conditions that I want to discuss. Well, let us break here and discuss it in the next class. So, but what I would like to show, I'd like to you to see, is that even with a simple model like this, with just two variables, and the nonlinearity is so simple, it's just a cubic nonlinearity, right? You can make plots and observe whole thing. You can really see how we are getting the kind of dynamics we are getting. So you can see why the neuron is producing the kind of dynamics, right? In terms of the phase plane and the null flights. Okay, so there are two more conditions which must be discussed, and let's discuss in the next class. And there will be an assignment based on the Fujinogo model because it's a very important model, right? Which we will announce maybe next week sometime. Okay, so thank you.
Yeah, I think, sir, there was a question actually by Ranjit.
Oh, okay.
He put it in the chat box. Like, isn't it more empirical than the HH model, Hodgkin-Huxley model?
Yeah, okay, good question. So HH model is actually formally derived from the measurements from the discrete axon, but it's hard to analyze. So they have simplified it. It's not more empirical. It's actually more theoretical. It is possible to do more theory with. It's very hard to analyze HS model theoretically. I mean, just imagine to do bifurcation analysis in 4 dimensions with
Yes.
such a highly nonlinear system. It's very hard. But moment you go 2 variable, I mean, and it's continuous differentiable systems, you can do complete trace plane analysis. So it's a major development. It's so it's theoretical, not more empirical.